Here we go with Unit 4, Lesson 2 for another day in Math 8. We're going to be keeping the equation balanced. Today we're going to introduce the concept of solving equations, but we're going to be looking at it from the perspective of a hanger. That's right, a hanger, like a hanger that you put your clothing on, kind of like what these socks are on right here below. We are going to recognize how equations are kept balanced is ultimately the thing. We're going to do it with a little bit of drawing and I hope a little bit of fun. So very first thing, take a look at this picture. What do you notice and what do you wonder? I'm going to have you respond to that in your homework, so don't skip that problem. Hanging blocks. When we talk about hanging blocks, we're talking about, first thing, this cool interactive version. You can do one of two things. Either add in this web address right here. It'll take you to this little picture right here to work with this applet. Or you can likewise just go from the beginning right here and work off of the assignment that I've given you, lesson 2, and you click on that link and you view that assignment. Should take you, well, to the wrong spot. Sorry about that. I forgot that doesn't take you to the same place when I click on it, but it will take you to this one right here. And you have the same opportunity with these pieces. You'll see the same picture. What do you notice and what do you wonder? Remember, the ebook is always a resource for you to be able to use. Hopefully it doesn't take as long as mine to load. If it does, or if it takes longer, I apologize. Same question about the socks. What do you notice? What do you wonder? And then you get into this one. And the cool thing about this tool is you have the opportunity to go ahead and work off of the same hanger. Just a little bit different than this page. I'll show you first on this one. Is if you take, so Elena has this triangle or this balance right here. It represents a hanger that is balanced because the weight on both sides is the same. And you might be saying, you're out of your mind. There's 3 squares on the left and 2 triangles. Where on the right, there's only 1 square and 5 triangles. Keep in mind that both expressions don't have to look the exact same to be equal. It is possible that some of these triangles combined together have the same value as 1 square. So let's keep that in mind as we go through this and let's figure these pieces out. So Elena does this. She takes 2 triangles off the left side and 3 triangles off the right side. Will the hanger still be in balance? Or will it tip to one side? Which side? Explain how you know. Well, right here in the little apple, we can go right here. If we take off 2 of them right here, well, 2 minus 2 is 0. And it takes away those 3 triangles. And you take away the 3 triangles on the left, gives you 2 triangles. And you clear those out and now unlock the hanger and we find out that it's unbalanced. You can leave it in unlocked mode where we see like this from the beginning. You can go ahead and click on unlocked and go ahead and take out those 2 hangers and we see immediately we're unbalanced. And on the right side, we take away 3 triangles and we see, 3 triangles, not 2. And we see that we're still unbalanced simply because we didn't take the exact same weight off of both sides. Flip side of this is you have this exact same problem here on the ebook version and you click on this web sketchpad and it's set up to do the same thing. I like this one a little bit better simply because it has these bars, but you still have the opportunity to lock it. Notice that there's a lock there, or unlock it. So it will currently, as an unlocked version, we'll show it as what it may be. You might want to do one or the other. Unlocked, take off 2 triangles and we see immediately we're unbalanced. And on the right side, we took off 3, 1, 2, 3, and again, we're unbalanced. You might have noticed there that as I took off 2 of them, we stayed balanced. That's because we took off the same amount from each side. Makes pretty good sense with that piece, okay? So the rest of these as we go through, if you can find another way to make the hanger balanced, go ahead and play with that to do so. In the page that we have right here, you can also do this by simply drawing what's going on. You can take off 2 triangles from the left, and then you can take off 3 triangles from the right. And what we can immediately see right here is I didn't take off the same amount of weight from each side. So I should know, well, this is not going to still be balanced. Which side will it tip to? I took more off of the right side than I did the left side. So it naturally should tip down to, on the left side, should tip down a little bit more because I took less weight off, making that left side heavier. So here's a question for you then. If a triangle weighs 1 gram, how much does 1 square weigh? Well, we can take a look and see with these pieces and figure out what will make this balanced or keep this balanced. If we're talking about the triangles, this triangle is 1, this triangle is 1, 1, 1, and 1. All the triangles equal 1. But then the question is, well, how much is a square? At this point, I don't know. So how can I find out? Well, I can use some guess and check, and I can think about it. Over here, I see 2 triangles. Over here is the only difference here, and then there's 1 triangle here. And if I take those ones away, I see 5 triangles for 3 squares. And then I start doubting myself and saying, oh, wait a minute, 2 triangles to equal. I don't think that's right. You can go ahead and play around with that. I'm not going to tell you can't, but I would like you to think about a couple of other pieces, a couple of other options. What if I only took away 1 triangle here and 1 triangle here? That's still balanced. And then what I have left is I have 3 squares and a square here. Well, what if I take off a square from each side as well? And then I look at this, how can I keep this balanced? If I take off 2 triangles here, what I'm left with now is 2 squares is equal to 3 triangles. I can see the same result, and what we're working towards is working on writing equations and solving equations that represent the same thing. So what I would make my conjecture with this is if there's a way to make these equal to each other, well, it's by taking off equal amounts or adding equal amounts to both sides. See if you can figure out how much does a square weigh. In this case, I'm going to be looking, when I came down to the very end, I saw 2 squares is equal to 1 or is equal to 3 triangles. And if I'm talking about 2 squares equal to 3 triangles, sorry, let me cover that up better. That would mean that I have 3 divided into 2 equal sized pieces. That means that 1 triangle is going to be equal to, or 1 square is equal to 1 5/10 grams. The other way that I'm talking about doing this is we can write an equation. If we look over here, that's 1x plus 1x plus 1x. So we have x plus x plus x plus 1 plus 1, because the triangles are all equal to 1. And then on the right side, we have x plus 1 5 times. Now, it's kind of silly to write an equation like that. I know that you're thinking, well, why didn't you just write it like this, of 3x's plus 2 for the triangles is equal to 1x plus 5 for the triangles, and you would be absolutely right. So now the question, thinking about what I talked about earlier, is how could I maintain balance? Think about what we did earlier. Let's go ahead and get rid of these so we can go ahead and find out how can I keep this balanced. Well, if we take a look at the triangles here, if I take 2 triangles from this side, from the left, I would have to take 2 triangles from the right, and that would keep it balanced. So we would show that, take away the 2 that I had on the left, the 2 that I had on the right, and what we notice is that that balance is taking away 2 units from this expression on the left, leaving us with just the 3 squares, or 3x. Over on the right side, we still have 1x that's left there, and we have 3 triangles for a value of 3. Cool. I'm a little bit closer to figuring out what 1 square weighs. On the next part, I don't have any more triangles to take away on the left, so I'm not going to try and take any more from the right. I do have a square that I can take away on the right side though. So let's go ahead and take away 1 square here on the left, taking away that x, but we have to remember to take 1 away on the left side as well to maintain our balance. And then what I'm left with is 2 x's on the left and 3 single values, 3 triangles for a total value of 3 on the right side. And then my last piece is just to compare the squares to the triangles. And as I said earlier, I have 2 squares that are unknown. If I divide those 2 squares, so I just get 1 square by itself, and I equally divide by 2 on the left side, I find out I have 3/2 of a gram, or 1 5/10 for x, making my 1 square weigh 1 5/10 grams. Pretty cool. We'll go through the rest of these a lot quicker. 2.3 is more hanging blocks. Again, there's an interactive version that you'll find on the ebook or on the other link that's given right here. A triangle weighs 3 grams and a circle weighs 6 grams. Oh, that's kind of cool. Find the weight of the square in hanger A and the weight of a pentagon in hanger B. I think it would be helpful to go like this. A triangle weighs 3 grams. So go ahead and label 3. And a circle weighs 6. 6, 6, and 6. Over here on the right, I see a whole bunch of squares and just one circle. So now I have to think, what is unknown here? Well, the value of the square is unknown. So we're going to say let the squares be equal to x. And I have an x here, and each of these are x's. What I want to do is go ahead and combine the values that I know. On A, I know that I have 1x. It's right over here. I'm supposed to find the weight of one of these squares. So if I was to work my way through this, what could I take away? What could I do with this? I have a couple of options. I can take away a circle here and a circle here, and that maintains balance. And I can take away an x here and an x here, and that maintains balance. When I look over here, what's left over, I see combined total. I have 6 and 6 and 3, so that makes it 15. And then, so 12 plus 3 is 15. And then I have just 4 x's that are left, which means that I have, for those 4 x's, I have to divide that evenly across 15. And I find out 15 divided by 4 is not quite 16. It's 3 and 75 hundredths is equal to x, meaning that the weight of a square in hanger A, squares weigh 3 and 75 hundredths grams. Hanger B, let's look at the same thing. Triangles are 3. Circles are 6. And when I look at these pieces, if I start to take away some stuff, I take away a circle here and here. I take away, oh, wait a minute, there's no more circle. Oh, but wait, if I take 2 triangles here, that's 6. And I can take that circle, that's 6. And then I find out that the pentagons, actually, I'm not going to try and draw a pentagon, but I actually see that I'm left with just pentagons, which were unknown over here. Let's call those y, just so we're dealing with different variables. Y, I see that 2y is equal to 2y. So what's the weight of a pentagon in hanger B? Well, I know that the pentagon weighs as much as the pentagon. So what is the actual weight? It's kind of an unknown value right there still. It could be anything, and it will always be equal to each side. So what we have with this one, the weight of a pentagon is all real values. Is really anything. It's kind of cool, right? So then let's think about, how am I going to write these equations? Well, for this one here, for hanger A, I'm looking at combining my terms over here. I have a single x, so I have x plus the weight of the others, which is 6 plus 6 plus 6, which is 18 plus 3 more, is equal to 21. So combining those like terms, because these are all constant values, we know their weight, but we don't know this one. And then we look on the right side and we see that we have 5 x's and a constant value of 6, because I know its weight. And then from there, there's my equation to represent the hanger. Hanger B, we said that the pentagons would equal y. We see 2 times y plus 12 is equal to 2 times y plus 12. And then what we recognize is that both expressions are exactly the same, which means no matter what I plug in for y, I will always maintain balance. In B, just a little sneak peek for that, this is what we call infinitely many solutions. That means there's an infinite number of answers that can be correct. But you notice for A, we came down, there is only one solution that will ever be correct for this situation for A, and there's an infinite number of solutions for B. Sneak peek what's to come down the road. On the next problem, are you ready for more? Go ahead and take a look at that one on your own. Give it your best shot and have some fun with it. I will tell you with this, what is the weight of a square on this hanger if a triangle weighs 3 grams? Again, just start by labeling and recognize the square is unknown. Give it a shot. write some equations, see if you can solve them. In summary, what we're after with this one is you know what, I just can't leave it alone. Let's go ahead and look at it a little closer. I have x plus 3 plus 3 plus 3 is equal to x plus 3 plus 3. There's a lot of ways that I can write this. I can look at this and I can call that 2x plus 9 is equal to x plus 6. That's the most obvious answer. Here's the other thing I can look at though. I can just get rid of one of these x's on both sides. Like eliminate one square here, one square here, and I'm just simply left with x plus 9 is equal to 6. That's another way to look at it. Or I could go from the beginning and I can eliminate a few of these triangles. I could take 2 triangles from here and 2 triangles from here, and then I would be left with over here, I would have x plus 3 is equal to x. All 3 of these different equations represent the exact same value. They're all different approaches to this. They will all get me closer to understanding what the square on the hanger is. All I have to do is figure out what x is. Be careful on this one and think about it with how that answer would have to work in order to be correct. Okay. If we have equal weights on the ends of the hangers, then the hangers have to be in balance. If there's more weights on one side than the other, then they're going to tilt to the heavier side. Every single one of these hangers represents an expression. When we're looking at an equation, I want you to really understand that an equation is a comparison of 2 unique expressions that are said to be equal. Or we're going to say said to hold an equal value. That, I think, is one of the most important things that we can recognize. In the past, I think you've always been taught that the difference between an expression and an equation is an equal sign. While that's true, there's a lot more to it. In this case, what we really need to understand is that each of these hangers on each side is an expression. This expression right here is not equal. This is what we call an inequality. What we recognize is if these triangles are all right here, we would see that 3t is greater than 1t, simply because it's heavier on this side. If we look at these triangles, we have 3t here and 3t here, which tells me those expressions have the exact same values. On this one, we have 1t right here, and then we have 3t over here. Clearly, this side has more weight, so we can see that that's the heavier side. All in all, what we're after with this, we can think of these expressions and balances as a metaphor for an equation where we talk about the expressions just like what I talked about. They have equal value, just like the balance on the hanger. If we're giving different values, saying that the expression here on the left is going to be, let A be the square, B be the triangles, then we see that A plus 2B is equal to 5B. And if we have a balanced hanger on each, we have to add or remove equally from each side to maintain the balance. If we don't maintain the balance, then we no longer have any equations. We can do these moves with equations by adding and subtracting the same amount from each side of the equation to maintain equality. But guess what? We can also use division and multiplication as well. All of these are the operations, and what we call all of this all together, and what you'll learn about, is what's called inverse operations. And using inverse operations is how we solve equations. It's also how we solve inequalities. Thanks for hanging in there. I hope you have a great day today. Let me know if you have any questions. Don't you dare give up.